So this is a relatively straightforward task, but do stick around to the end for some thoughts on efficiency and optimization. So it's something that I found online. Quite often I find tasks, or I'm inspired by things that are tweeted, for example, by maths teachers, and I think this might be one of those. I can't remember exactly where I got it from. And I don't like the wording particularly, but I've just included the original task as is. So find a two-digit positive integer that becomes 7 times smaller when its leftmost digit is removed. So I don't like the term 7 times smaller, or the expression 7 times smaller, but what it means is it becomes a seventh of the original size. So I would start off with it. Just think of an example here. So if I take it's taking, say, a two-digit number. Okay, so let's take 25, for example. And I'm going to remove, so what we're doing here, when its leftmost digit is removed. So I'm going to remove the leftmost digit, so that's removing the tens to leave the units, and it's always going to be the tens and the units because it's a two-digit number. Is that a seventh? So is 25 7 times 5? No, it's not. So that's not the answer, but that's basically the idea. So look at keep the units, and is the original number 5 times the new units value? So there's two things that we need to kind of think about here. We need to think about, one, how we're going to do that test. And secondly, which numbers are we going to apply that test to? So this is going to be a program solution. So it's going to be like a brute force solution. You probably could do it algebraically, but this isn't a math class. We're going to have a look at a program solution. Computers are very fast and good at repeating things, so we're just going to try various different combinations. So first of all, how are we going to remove parts of the number? So because it's talking about the leftmost digit, your first thought might be that we could just cast that to a string maybe, and then just chop it up using string slicing if we're having a look in Python. So if we say something like number equals 25. So quite often when I'm programming, I'll just start off with a fixed value, and what we'll do is we'll pop this into a loop later on so we can vary that number. But let's try it. So we could say, well, let's make that a string. So we can use str, remember? So all of the Python variable types are actually commands in themselves that you can use to convert or cast different types of variable into that type. So str number will turn number into a string, and then you might be familiar if I just run that. So you can use the others. Some of them don't make sense, obviously, but you can do it the other way around. So you can say int 25, for example. If you're not sure what they are, there's a Python command called type, and you can apply that not only to variables but to actually kind of literal values as well. So if you say type hello, it's going to say str short for string. And if you say type, 1, 2, 3, 4, it's going to tell you it's an integer and so on. And each of those things that it reports back are actually keywords in themselves for casting into that type. And then when we're looking at text, so I'm just going to say a equals hello, not a meaningful variable name, but it doesn't actually mean anything anyway. Remember that a string, which a is, so if I say type of a, it's going to tell me that it's a string. A string is literally a string of characters, a series of characters, and we can refer to the individual characters by number. So they're all numbered starting from 0. So A0 is the first letter, and so on. We can refer to sections of text. So we can say from 0 to 3, for example. A quirk of Python is that that's not inclusive, so it's up to, but not including 3. So it'd be 0, 1 and 2. So it will be 3 characters, the H, the E and the L. You can also, if you want to start at the start, you can just miss out the 0. So you can do that, which is more probably useful in other circumstances. If you wanted to look at characters at the end, you could use len, for example, to look at the length of a particular string and then subtract that. Just subtract the number of characters you want from the end of that. But actually you can use a negative number as well. So if you say -1, it'll be the character on the right. 1 in from the right. There's no -0, so we do start counting at 1 on the right hand side. So we could say something like this. We could say the units, which is what we're picking off, is number -1. So that means the rightmost character. So that's the same as removing the leftmost character, keeping the right one, because it tells us in the question it's a 2-digit number. So that's fine to do that. And then what we want to do is we want to see whether that is a 7th. So is the number, so we're just doing a test then, aren't we? Saying, so we want to say if the original number, now the original number is now a string, isn't it? So actually we want to turn the original number back into a number, and then we want to say, is that equal to 7 times again, we need to turn units, because units will be text because we chopped up a string version of the number. So is that a 7th? And then we're going to, so that checks whether it's true, and then what we want to know is, what's the actual question? Just whether we found it. So it's going to be yes or no, isn't it? So is this property true of that number? So if the units are a 7th, so if the original number is 7 times the unit value we just found, then we've found the answer. So if I run that, obviously it's saying no, and we've just seen on the whiteboard that that's not the case. So that does work, but there's a lot of converting backwards and forwards and casting and things. And not only does that make the program longer, but obviously it takes longer for the computer to do. It's not a particular task, but you might have seen my blog on using a very slow computer. So if you were using a 70s, early 80s home computer, this might take a more appreciable amount of time than it does on a modern device. So another option that requires less converting backwards and forwards is to use modular arithmetic. So what modular arithmetic is, it's a division with a remainder, like you did back in primary school. So if I said, what is 10, the symbol in Python is a % symbol. If you're looking at exam reference language in an OCR GCSE, for example, it will be the word mod, as it is in BASIC. So what that means is, if you divide 10 by 3, what's the remainder? So 3 3s are 9, so the remainder will be 1. So why is that useful in this particular case? And in fact, it's also useful in converting between other number bases. So there was a hexadecimal question in a previous paper that used a similar technique to this to separate out the 16s and the units. So if we divide a number by 10, so obviously if I have 25, for example, in my example over there, so 25 divided by 10, it's 2.5. That's not particularly helpful, but what that is, it's 2 lots of 10 and 5 left over. So if I do 25 mod 10, it just gives me the units. So that's a shorter way. We don't need to convert backwards and forwards. We're keeping the number as a number, and then we can do the numerical check more easily afterwards. So I'm going to separate this out. I'm going to separate out the units by saying it's the number mod 10. Now we don't need the other part, because the question, it just asks us to remove the left hand digit. But if we did want to check what the left hand digit is, so notice in this case, when we divided by 10, kind of the whole number part was the number of was the number of tens, wasn't it? There's a similar calculation called integer division. So if I did 25 and it's a double slash for that, and that just gives me the whole number part. So if you use those two things together, going back to my original 10 divided by 3, so if I do 10 integer division, so that would be div in exam reference language, so that would be 3, and then 10 mod 3 is the 1. So those two numbers together, 10 divided by 3 is 3, remainder 1. So that would be the 3 would be the, not in this case, that doesn't convert to different tens and units, but in this case we could use integer division to get the tens. So now we can do the same test. We can say is the number, and we don't need to convert it to an integer, it's already an integer, is it 7 times the units that we've just taken off? And actually I'm quite a fan of doing things in line, so I might just stick that bit there straight in there and not bother. Just make my program a little bit shorter. And also save a bit of memory, because actually if we don't need to store units, what's the point in keeping it? So 7 times, and not sure of the operator precedence of there, but I'm just going to put that in brackets to make it more readable. Okay, so if that's true, then what I'm going to do, actually thinking ahead, so when we try this on different numbers, we're not going to want to know yes or no, but we're going to want to know what the answer is, isn't it? Aren't we? So we're going to say we'll just print the number. So in this case, it's not going to print the number because it's going to print nothing, isn't it? There's no else. And in fact, I've got my extra equal sign. Okay, so it doesn't look like it's done anything, and that's because there's no alternative, but let's just stick an else in for testing purposes. So print no. So run that now. So that's a no. So it's failed the test, but what we just want to do is print out the matching number. So if we go back to the whiteboard, we've done that first bit. How are we going to do the test? So we looked at string slicing, but actually you can use modular arithmetic just to pick out the units. And so once we try this on all the different numbers with our kind of brute force method, then it will print out the ones that match. So we're going to repeat this. So which numbers are we going to apply the test to? So it's always worth thinking with something like this. Do we know how many solutions there are? And when are we going to stop? So in this case, there's not a lot of 2-digit numbers. But if we were saying, of the first billion numbers, is the one where this is true, obviously there'd be a lot more to check. And so we might want to stop when we found one. However, it doesn't say there's only one solution. So there might be more numbers to check. So in that case, we do want to check all of the possibilities rather than. So I'm going to use a count controlled loop rather than a condition controlled loop, because I want to check for all possibilities. If I knew there was only one, I could use a condition controlled loop and just stop when we'd found it. So what I'm going to do here is I'm just going to indent that section because it's going to be repeated. So rather than saying number is 25, I'm going to create myself a loop and vary that value. So I'm going to say for number in range, and it says in the original question that it's a two-digit positive integer. So I'm just going to loop through the values. So 2 digits, that's from 10 to, well, obviously 99, but Python always stops one short, so I'm going to do that. So I'm going to have for number in range 10 to 100. So it's going to try all the numbers from 10 to 100. And if that test is true, then it'll print the answer. So let's see what that does. Okay, so it's found one, 35. There is only one, as it turns out. 35, is that true? So we remove the first digit, so to leave the 5. Is 5 a seventh of the original number, or is the original number 35, 7 lots of 5? Yes, it is, isn't it? So that's worked. So it might look like job's done there, and if you're used to using a modern computer, you might think, well, okay, I've finished now. But I think there's some more things that you could think about when you're doing this task. So how many times, and this might come up as a question on the written paper, so how many times are lines 2 and 3 repeated? So if we're counting from 10 to 90, 10 to 100, that's 90 repetitions, isn't it? So it's doing this test 90 times. Okay, and that's not a lot for a modern computer. It takes an imperceptible amount of time to do that. But could we speed that up? It's always worth thinking about, efficiency and how long your program takes, because it might be, like in this case, we're using a shared resource. So if everybody's programs on Replit took a lot longer than necessary, that's going to slow the whole thing down. There might be programs running concurrently on web servers, for example, or you might be slowing down somebody else's web service. Or even just running on a computer. You've probably got several applications running on your device at the same time now. So if one hogs the processor, that's going to take processing power away from the others. So could we reduce that number from 90 to another value? Well, let's have a look at the question. Let's have a little think about that for a minute. So it's a 2-digit number that becomes 7 times smaller. Okay, so 2-digit number. So when we divide it by 7, it's got to be a whole number, hasn't it? So what does that tell us? That tells us that the number that we try has got to be a multiple of 7. So, we could use that. So we could go up in 7s, couldn't we? But actually, for that to work, so if I run that now, if we just think about just going up in steps of 7, actually it's not going to find the answer. And why hasn't it found the answer? Because it doesn't start on a multiple of 7. So it's going to go 10, 17. Well, 17 is a prime number. So actually, we need to start on a multiple of 7. So if I start at 14, go up in 7s, I'm only going to hit numbers that are divisible by 7. So that's reduced the amount of repetition quite considerably. Let's try that. There we go. And it still finds the answer. So I obviously didn't click the button properly there. Okay, could we reduce it even further? Well, if we're starting off with a 2-digit number and we're taking a digit off, that means we've got a 1-digit number. So the biggest 1-digit number is 9. 7 nines, it's only 63. So actually, we don't need to go all the way up to 100. We only need to go up to 63. Remember, we have to go 1 more in Python because it stops 1 short. So if we run that now, still finds the answer. Probably slightly quicker. It's a bit difficult to tell with Replit because it's running online. But that's a lot fewer repetitions. So it's carrying from 14. So it's doing 14. It's counting up 49 in steps of 7. So that's only 7 checks rather than the original 90. So that's a lot less work for it to do as well. So it's always worth having to think about when you find a method that works, actually, are you trying too many combinations? Because one of the things that causes programs to slow down is unnecessary repetition. And doing 90 lots of repetition rather than 7 is obviously quite a lot more than 10 times as long, won't it? So things like that are definitely worth thinking about as well. So on the face of it, this is quite straightforward, but there are some things you can think about when you get to the end, and sometimes there are multiple ways of doing things.